Welcome all, I am Preeta Vijay and today I'll be presenting our work TriRE, a multi-mechanism learning paradigm for continual knowledge retention and promotion. This is a joint work with Prashant Bhatt, Ilahi Arani and Bharam Zunus. Continual learning systems frequently grapple with the stability-plasticity dilemma. It refers to the need for neural systems to strike a balance between maintaining stable representations of previously learned information while remaining flexible and adaptable to new knowledge. In recent times, researchers have put forward several strategies to mitigate this. It can be broadly categorized into three families of methods: parameter isolation based, weight regularization based, and experience rehearsal based. While these approaches have their merits, they are not without limitations, such as capacity saturation, class discrimination challenges, and overfitting on buffer data. In stark contrast to this, the human brain manages continual learning seamlessly by orchestrating a dynamic interplay of neurophysiological processes as mentioned here. So, in this work, we hypothesize that by harmoniously integrating various neurophysiological aspects into continual learning, instead of treating them as independent competing methods, we can develop a more comprehensive solution to address the stability plasticity dilemma. Therein, we introduce retain, revise, and rewind, a novel learning paradigm designed to effectively counter the challenge of catastrophic forgetting in DNNs. We will be looking into each of these phases in more detail now. Firstly, in the retain phase, we draw inspiration from the human brain's ability to utilize context-dependent gating for selective filtration of neural information. Through this phase, we engineer task modularity in our model. This is achieved by first training a hypernetwork and subsequently extracting a subnetwork, which embodies the essential knowledge of the current task. To extract the said subnetwork, we employ activation pruning followed by weight pruning. Next, the revise stage also takes cue from biological phenomena such as neurogenesis and metaplasticity. This stage predominantly centers around the revision and solidification of knowledge residing within the extracted subnetwork of the current task and the cumulative subnetwork from past tasks. Joint fine-tuning of these networks enhances knowledge overlap and forward transfer. The outcome is a more comprehensive representation of all the seen classes. Finally, in the rewind stage, we are inspired by the brain's ability to actively forget and relearn. This process involves rewinding the weights not in the cumulative subnetwork to a state where it has already acquired vital features and knowledge. These rewound weights are then fine-tuned for a few epochs, which reactivates these less active neurons and prepares them for future learning tasks. Now looking at the table, we can see that our results here underscores the effectiveness of TriRE, emphasizing the importance of blending various families of CL methods to tackle catastrophic forgetting rather than approaching them individually. We can see that while some other methods excel in simpler datasets, TriRE maintains a competitive edge, particularly evident in challenging scenarios like sequential tiny ImageNet dataset. Now, through the ablation study, we delve into the individual contributions of each phase. For instance, we see that the retain phase primarily targets task interference reduction but may not offer the best forward transfer, or that the combination of retain and revise effectively solidifies knowledge, however, it encounters capacity constraints. Nevertheless, our results consistently show that the synergistic integration of all three stages yields the most robust outcomes across both datasets. Now, to conclude, we saw that TriRE takes inspiration from various neurophysiological processes within the human brain. Each task is thoughtfully divided into three stages, namely the retention of active neurons, knowledge revision, and the promotion of less active neurons for future tasks. By combining these stages harmoniously, TriRE substantially reduces catastrophic forgetting, clearly outperforming other continual learning methods. Now, as we look into the future, our research aims to address the limitations of TriRE, such as reducing computational memory overhead. We are also exploring ways to adapt the method for task-free continual learning scenarios to enhance its capabilities. Thank you.